Here we are, ready for section 7.1, the last chapter in this book of ours, and the shortest chapter. They kind of cram a lot of stuff in a couple of sections. This whole section is about sequences. We're focusing both on arithmetic and geometric sequences. And then our next section, 7.2, is on series, which is where we take the numbers in a sequence and we add up them together. Alright, so a sequence is an ordered collection of events or numbers or objects or something like that. So let's look at a couple of examples. We have some numbers called triangular numbers, which is where we can organize our geometric objects, in this case circles, into a geometric pattern of triangles. This is similar to how bowling pins are set up. When you have your 10 bowling pins, it's like this 10 here. So the pattern is you start with 1, and then you have 3, and then you have 6, and 10. So each time we're adding an additional pin or an additional object to our triangular number. So 1 plus 2 is 3, and 3 plus 3 is 6, and 6 plus 4 is 10. So our next number is 10 plus 5, which is 15, and 15 plus 6, which is 21. You guys can draw those out if you'd like to. Our square numbers is a similar idea, but it's the number of objects that would create a square. It can also be called the perfect squares, those numbers that go with those visual square objects. So start with 1, and then to get the next square up that has sides 2 by 2, it would be 4, and then 3 by 3, which is 9, 4 by 4, which is 16. So obviously the next steps would be 5 by 5, or 25, 6 by 6, or 36, and 7 by 7, or 49. Term. Term is the word we use to refer to each number in the sequence. So 1 is a term, 3 is a term, 6 is a term, 10 is a term, 15 is the next term, 21 is the next term after that. So this is the first, second, third, fourth, fifth, and sixth term number. Okay, an infinite sequence is one that goes forever. And the way that we can tell an infinite sequence from a finite sequence, notice if I take the word in off of the front, finite, it ends. There's 3 dots that would tell us that it keeps going indefinitely at the end. You know, the little ellipses, dot, 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 right? Not to be confused with an ellipse. I don't know if you've heard that term before for the dot, 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 and ellipses. Anyway, that tells us it goes forever. Alright, so we have some examples here. We need to learn about the different types of sequences. Oh, I get it. So I was just jumping the gun when I labeled some of these as arithmetic or geometric. We'll get to that. I'm going to clear this out and we'll just start fresh. So the first sequence here is a famous one named after a guy who kind of discovered it in the 1100s in Italy. So he was from the city of Pisa and lived around the time the Tower of Pisa was being built, about 800 years ago. So this one's formed by adding 2 numbers together to get the next number. And then you repeat that process. So add the 2 numbers together to get the next number. Add these 2 numbers together to get this number. And this process continues. It's a very cool sequence that we can find in nature and architecture because it forms what we call the golden ratio, the ratio of the numbers. It's called the golden ratio, and it's just pleasing to the eye. So it's used in all sorts of ways, as well as just occurs naturally. There's lots of awesome videos out there about this sequence. So this is called Fibonacci sequence, and it just comes from taking 2 terms, add them together to get the next term, and repeat. Alright, next we have 1 to 3 to 6. We just saw this one, right? It's adding 2, and then it's adding 3. So the number we're adding each time is incrementing. We could also call these the triangular numbers if we wanted to. We just saw that on the previous page. Okay, and then this one we barely just saw as well. So we're supposed to find the next 2 terms. I skipped that part. So if we add 21 plus 34, we get 55. And then 34 plus 55 is 89. So that's the next 2 terms of that sequence. This one, we would bring this up to 21, and then we add 7, so the next one would be 28. Next, we have those square numbers, so 2 more terms would be 6 squared and 7 squared, so I'm just going to call these squares. If you can figure out a way to actually write a formula for any of these, that would be great to start practicing that, because we're going to be doing that today with our arithmetic and geometric sequences. So we're going to use n, we'll learn about all this in a second, n for the terms. Actually, we use n for the term numbers. So like n equals 1, that's the first term number, n equals 2 is the second term number, n equals 3 is the third term number. So what can we do to n to get these numbers? Well, we can just square it. So these can be found just by doing n squared, and that would give us a formula to find the numbers in our sequence. So for example, if we wanted to find the 10th number, we could just go 10 squared and get 100, and that would be the 10th number of our sequence. The formulas for these two are more complicated. I'm pretty sure our book has a formula that can be used for Fibonacci sequence, but it's quite complicated. Triangular numbers, really these aren't formulas we're going to worry about right now. We mostly want to focus on 2 types of sequences known as arithmetic and geometric. This one here, from -7 to -4 is adding 3, and then -4 to -1 is adding 3. So we can see that repetition of adding 3 each time. That makes this have a bit of a linear property to it, where it's going up by that 3 amount. That's kind of like your slope. It's going up each time, right? So our next 2 numbers would be 11 and 14. And because we're adding the same number each time, we are creating what we call an arithmetic sequence. Like I said, we'll talk more about that here in a second. This one, let's see, we've got 64 and then 32. So half of 64 is 32. Half of 32 is 16. Half of 16 is 8. I'm pretty sure that these numbers are being multiplied by 1/2. So the next 2 numbers would be 1 and 1/2. So we're multiplying 1/2. And when we multiply a number to get a sequence, we call that a geometric sequence. These should be clear back stuff you learned in 9th grade. Okay, 37, 32, 27, 22, 17, 20, 12. I feel like this one is subtracting 5, right? So subtract 5, or we could think of this as adding a -5. Just by definition. So this is actually another arithmetic, because it's adding the same number over and over, even though that number is negative. It's like having a negative slope, or our values will go down instead of up. All right, I wonder what's happening in G. Let's see, 81 to 54 to 36. Do we see something consistently happening? I don't feel like there's a consistent amount being subtracted from each one, so this could just be some sort of ratio. Let's go ahead and see if there's some sort of ratio. When you're looking for a ratio, you would take this number, the one past a number, and then the one before that number, and divide them. So I'm just going to see if we can get a common ratio out of these. So both 54 and 81 are divisible by 9, correct? So 54 divided by 9 would be 6, and 81 divided by 9 is 9. So we can actually go further than that. This is 2/3. This is a 2/3 ratio. If we multiply 81 by 2/3, we should get 54. If we multiply 54 by 2/3, we should get 36. Let's see, 2 times 54 would be 108. And then is 108 divided by 3 36? I believe it is. Let's see, 36 times 2 is 72. Divided by 3 is 24. 24 times 2 is 48. Divided by 3 is 16. I think we found it. So 16 times 2 is 32. Divided by 3, well, that's an oddball number. 32/3. And then we would have 64/9. So our next 2 numbers are a little bit complicated. We are multiplying the same number each time, even though it's a fraction. It's the same number being multiplied over and over. So we call that a geometric sequence. What about this one? I think this has a whole different type of pattern. This one is more like the numbers themselves are being used in the fractions. So like we have, if our starting n value is 1, and then our next n value would be 2, we kind of have an n over n plus 1 pattern going on here. Only it's also going to be flip-flopping as a negative, so we would also need to multiply that by a negative each time, depending on whether the number is odd or even. So if I do n over n plus 1 times negative 1 to n minus 1 power, what that'll do is this first term, n is 1. So 1 minus 1 would be 0, and negative 1 to the 0 power is just 1. So that would be 1, which is positive, times 1 over 1 plus 1, which is 1/2. Let's go to our second term and see if that works. So our second term would be 2 over 3, but then we plug this, multiply by this thing, so negative 1 to the 2 minus 1 power, so that would be negative 1 to the first power. That means we're multiplying this whole thing by a negative 1, and that'll give us this next answer, right? So our next two answers, we don't actually have to use the formula for that. We're going to have a positive 5 over 6 and a negative 6 over 7. And if you have a better way of explaining this besides this little formula I wrote here, that'd be great. This one is not geometric or arithmetic. It is just a weird sequence. Okay, what about this one? Is there a way we can multiply this by something to get this? I think so. What if we took negative 5 and we multiplied by negative 3/2? Because a negative times a negative would give us a positive, and negative 5 times negative 3 is 15. And there's our halves. Does it work if we try it again? So negative or positive 15/2 times negative 3 is negative 45, times the 2 on the bottom is 4ths. Yeah, I think that works. So this one would be geometric because it's multiplying the same number each time. So without actually explaining geometric and arithmetic yet, because those are topics you should have learned in 9th grade, we've kind of gone through and identified them anyway, and maybe you remember those concepts a little bit. Okay, I'm going to stop this and I'll go on to it.